Welcome back, Digital Logics. One of the best courses you had in your life. Lots of stuff. I know it's lots of stuff, and it's not finishing. And I say, oh my God, this is important too. That's very low, and you're gonna make money. Really, I hope you get enough to pass it. Okay, today we're gonna talk about last piece of the puzzle before going to sequential logic, memory, real computers. When you have state, then you have memory, and you can make decision not just from input, but from past. From whatever happened past, you can make decision based on that. That kind of systems are advanced systems, the type of systems that computers. Okay? So today we're going to talk about two new sequential, combinational, two remain combinational logics. Guys, you talk too much. Talk too much. I can't please. So first is priority encoders. We talked about encoders before. And if you remember, encoder was a combinational logic. Okay, the encoder was a combinational logic that had lots of inputs, like 2 power n inputs. This is decoder. And n outputs. Like D0, D1, and D3, and Y0 and Y1, for example. It's called encoder. Encoder. 4, 2, 2. This was encoder. So the problem with encoder was just one of the input need to be active. Just unique active input. For example, this can be 1 and the rest 0. So unique input data coming in, and corresponding that number is gonna encode it. Like for example, in this case, it's gonna make 0, 0. Why? Because it's for D0. Next time, for example, this is the input. And D1 gonna be encode. So we get some code and we encode it. Like in keyboard. In keyboard, you have lots of keys. And press 1, just one of them get on. And the ASCII code, that is ASCII. ASCII code corresponding to that key is gonna get encoded. But what is the problem? Sometimes inside the keyboard, you press 2 keys at the same time, or multiple keys at the same time. That's the application of priority encoders. If multiple input coming, which one is the best? The one with highest priority. So for some applications, we need to consider priority. Priority is one of the parts that always in computer we need that. Like for example, interrupt happening in computer a lot. And if multiple interrupts at the same time happen, the one with highest priority needs to get more chance to actually check first. Let's see how we can design a priority encoder. So normally when multiple signals happen at the same time, we need priority. Example, interrupt happening in microprocessor, yes. And the output represent the binary code of the highest priority action. Like for example, in that decoder that we talked about, like 422 D0 to D3, and Y0 and Y1. This encoder, for example, accidentally these two get on at the same time. But which number we're gonna choose as an output? The highest priority one. Highest priority one always is the most significant bit. The highest priority one is the most significant. So in this encoder, because this encoder is priority based, the highest one is number 1. So it's gonna make 1, and 1 is D1. That is 0, 1. Did you get the point? Here we had two inputs accidentally, but we consider the one with highest priority. One with higher priority means the one that is most significant in this case. Okay, so let's see how we can design this circuit. This was example. How we can write truth table for that? The truth table for that encoder, that priority encoder is like that. You have 4 input, D0 to D3, and 2 output. First, if all of the inputs be 0 is not allowed, because I said the unique input, one of them need to be active. If all be 0, this is not valid. If the first one is 1 and the rest 0, in this case it's gonna make 0. If it make second one D1 1 and D0 don't care, whatever, again what we consider D1 as the output, highest priority. If this is 1, we get D2 as the highest priority, and this one D3 as the highest priority. So this is the truth table for that. So that compared to the normal decoder, here we have don't care. It means we don't care the other lower priority bits. We just consider higher priority. And that's something that we make decision based off that. Okay, but the main point is this part, how we get from truth table to actually corresponding Boolean expression. First of all, y1. Okay, so pay attention for this part. So for y1, similar to the decoder, we're gonna check where in the output is get on in these two cases. And then for each one going to the input, that makes that 1. For decoder, we haven't had these x's. We just had 0, and we directly I can write, for example, D2 plus D3. But here is not like that. Because we have don't cares, we need to write even zeros as well. So here, it's D3 bar D2 plus D3. We consider this part as well because of this don't cares. And we can make that simpler. This is the rule that we have. If we have D3 here and D3 bar here, we can remove that D3 bar. And it's going to be D2 plus D3. Why we can remove it? You can expand this or in this and this going to get 1. So the result going to be this. Okay, what about Y2? Y2. You do it. I'm going to come and check. So first, what you're going to do, find where Y2 is, sorry, don't have Y2, Y0. Y0. What is Y0? So first, we need to see where Y0 is 1 in these two. And then go for corresponding input, but you need to consider zeros as well. Good. So it's gonna be D3 bar, D2 bar, D1 plus D3. Right? So D3 plus D3 bar, D2 bar, D1. This is coming from this part, and this is coming from this. And we can make that simpler, of course, because D3 and D3 bar here, we can remove D3 bar. The result gonna be D3 plus D2 bar D1. Y0. Y is yes. Any question? Yeah, this design of priority one is a little challenge and different than what you had before. But we have another example soon. We have 2 more examples. So this is a cleaner version. Something here that I can remove it. Okay, a 3 to 2 priority encoder. Right now, we want to design a priority encoder, get 3 input, D0, D1, and D2, and make 2 output, A0 and A1. Oh, and V. V is also in priority encoder, we always have it, that showing this is valid or not. For example, 0, 0, 0 is always invalid. So for for these inputs, the output is the valid is 0. So we don't care about output anymore. We don't need to check output anymore. It's not valid. Other than that, is valid. If it's valid, it works normal. So for 0, 0, 1, we create 0. For 0, 1, anything else, we create 1 because it's highest priority. And if it's 1, anything else, is going to make 2 y2 because D2. So we have this truth table, and we want to design, we want to find what is V, what is A0, and A1. First of all, let us start with A1, for example. And let I erase these tables and edit this. Okay. So we want to design A1 first. A1. Okay, so the step that we need to do, first we need to check the A1 to see where is 1. We just have 1, 1 in A1. So we just have 1. Corresponding input is D2. So it's D2. That's done. A0, we look at A0 to see where is 1 here. So the corresponding input, here we have 2. D2 bar D1. Good. And what about V? V is another input, but we have 3. We have 3, 1 here. Okay. For this one, we have D2 bar D1 bar D. For the second one is D2 bar D1. For the last one is D2. But simply we can eliminate some of them because we have D2 here and D2 bar here. We can eliminate this. And also the same way we can eliminate this one and this one. So the result is D1 plus D2 plus D3. Oh, sorry. D0, sorry. D0, D1, D2. D0, D1. That's it, D0. That's it. So this is how we design a priority encoder. Okay, don't worry, we have another example. Once we write that, you are done with this if you want to write it up. Here I also explain why. For A1, A1 is 1 only when D2 is 1. A0, when A0 is 1, when A0 is 1, this row, D1 need to be 1 and D2 need to be 0. I didn't write for W for V, but for V also is D0 plus D1 plus D2. Okay, so another example, 4 to 1 and V, because we already had 4 to 1 V dot V, but here is V. The rest are the same. For the V, I'm just going to compute for the V. As you can see, we have 4, 1 here. For the first one, is gonna be, for the first one, D0 bar, D2 bar, D1 bar, D0 plus, for the second one, D3 bar, D2 bar, D1 plus D2 bar, D1. Oh, sorry. D3 bar, D2 plus D3. And when we eliminate, this is gonna go because we have D3. We can expand that, and this is gonna go. We have D2 and D3, so these 2 gonna go, and we have D1, D2, and D3. These 3 gonna go. So the result gonna be D0 plus D2, D1 plus D2 plus D3. Easy. So that's gonna be valid output. So we always have valid output too, because for encoders, we always need to have one input. One of them needs to be active. If it's none of them active, that's not valid. Like in this case, 0, 0, 0, 0 is not valid input. That's it. That was about priority encoder. Any question about that? Okay, let's go for demultiplexer. Demultiplexer is also very fun. In demultiplexer, in multiplexer, we had some input and just one output. This is mux. Like, for example, 4 to 1, you have select. Multiplexer is used so much, we're going to use that. But demultiplexer is vice versa. So you get one input and multiple output based off select. Like you reverse it. So you get input, one input. This was output. This is input I. And the output D0, D1, D2, D3. This is Dmux. 1, 2, 4. This was 4, 2, 1. Let's see how we can design that. That's also very easy. Let's clear this one. Truth table for demultiplexer is like that. You have just 2 inputs, select, and also I, but I gonna be in here. This is how we design. So if this is 0, 0, I gonna go out as an output. Whatever I is gonna go out. So the design of demultiplexer is like that. We put I as an output. Whatever is I is gonna stay there. So it means Y0 is S1 bar, S0 bar I. What about Y3? Y3 is this one. Y3. This part of my screen getting Y3 is S1 bar. Oh, sorry, S1, S0, I. That's it. And for the rest, the same. So that's how we design the cleaner version. So that's the output. First one is input. Whatever is input is going to go to out based off these select signals. They are select input. Select input. But this is interesting. Demultiplexer is very similar to decoder. Why? Look at this. This is demultiplexer. One input coming, some select, and 2 power S gonna go out. So for decoder, we also had the same. We had S, for example, S1 and S0, and D0 to D3. This is demux. This is decoder. So decoder, imagine input is S0 and S1, and output is D0 to D3. However, we don't have input, but input here acts very weird. It's like whatever is I is gonna get out. So what about instead of what in decoder we have enable? In decoder we have enable. What about just connect I to enable? If we put I exactly enough to enable, these two are gonna be same. So designing decoder is similar to designing demultiplexer. Just instead of enable, we put in. We're gonna have this picture in next slide too, if you want. So here is explaining that. So demultiplexer has one input and multiple output using select, and decoder has no data input, but use select lines to activate one output. So we can design them similar. So that's the same picture that I grabbed there. Here also you can see that. So a demultiplexer is a decoder plus enable data input. Question. Imagine you want to design a demultiplexer 1 to 2 demultiplexer using decoder. Which decoder you need to use? Find the decoder corresponding to this demultiplexer. One input, D1S, and D0 and D1. What is the type of decoder you need to use to make a demultiplexer 1 to 2? So the S is important because I is always enable. So the decoder needs to be 1 to 2. 1 to 2 decoder. So the decoder in this case is one input, that is S, and two output, D0 and D1, and one enable. We always need enable, that is enable is I. So it means if I is 1, if I is 1, so the enable is 1, so the decoder working fine. And if select is 0, this one gonna go to 0. And if S is 1, this I gonna go here. Let's just try it for 0 to don't make mistake. If S0 is 0, let's see how this demultiplexer works. In this case, the enable is 1, and S0 is 0, so this gonna connect to that. Whatever is here gonna go in this. It's exactly the same. In demultiplexer also, if the I is 1, like here, and S is 0, so this gonna go to the 0. Same thing's gonna happen. So that's why these two are similar. These two circles are similar. That's it. That was everything about combinational logic. And next class, next week, we're gonna start with more amazing things. We're gonna have exam, not next week, but the start of the following week. So get ready for exam. For exam, we're gonna have whatever we had after first midterm. I'm not gonna do another questions about that part. Have a great day. Yes.
Everything's on GitHub, which is where I type it in, it'll be wrong.
Complete binary. That also complete binary. What I have is that add them and then add them together and then change them to that's the way that we do it. Make something wrong. Okay. So you said is bigger than 5? So just